Okay, we go for the differential postponement. Always known as a delay differential as well. So the timing, the timing of the differential in the supply chain. So there is the differential postponement, the timing, and then they have modular components versus final assembly for each model in the inventory. They have two principles. Two principles. They have different thing, differentiation thing, element must be concentrated in the one or few chunks. So they have I will explain with example later on. And then they have number two is a products and production process must be designed so that the differentiation thing chunk can be added to the product near end of the supply chains. They have two principles. So what is it? Okay, we go for this example. So you can see this in the textbook as well. They have this scenario. Scenario A, they call it early differential, and then scenario B is a postpone differential, delay or delay differential. So this scenario A and B, you can imagine as well as a printer just now. So we have different version of the printer, different version of the model of the printer. So if model, for example, they have a different adapter of power, and then they have because they have a different country to export. For example, in Japan, Brunei, in the US, they have different code of adapter. So because the power in Japan they have 110, in Brunei they have 240s, but in UK they have same but different code of the powers, different plug of power. So because of that, they need to consider at what point along the supply chain the product can be what I call it, the variant. They have three countries to export, A, B, and C. So different variant of the plug. So the printer, they have same printer, but differential only in the electrical power standard. They have three different geographical regions. So they need to segregate that one. They need to export to different, or they need to transport. The process inside this one, they have assembly, they have transportation, they have packaging, packaging to export. So they have divide by three process to explain this one. And then so assume that these three basic activity as a supply chain, and then these three basic activity have different for each scenario. For scenario A and scenario B, you can see different. So at the scenario A, the numbers they make assemblies through the printers. They transport based on for country number A, they transport to the inventory for number A. Country number B, they do a packaging and transport to the country the inventory at B. They transport to the inventory place or warehouse at the C place. So this will do at early differential. At the early stage, they do all assemblies, include the power code, electrical powers for the each printer, and they make a proper packaging before they do a transportation for the each inventories. All right, this is call it early differential. But for the scenario B, the components associated with the power conversion are assembled after transportation. This one after transportation, they do a sub-assembly here. They do a sub-assembly before they transport or they send to the customer or country or region required that printers. For example, this one for Japan, for Brunei, for UK. So they do a sub-assembly before they transport it. But at early stage, they do a assembly for the printer without fully assembly for the cord, for the power conversion assembly. So they just transport and then do this after one. So you can see here the different here. You need 3 transportation, different thing, 3 inventory, but here you have only 1 inventory, 1 transport, and then do a segregation before you shipping to the customer at the end, at the inventory side, at the warehouse side. So you can see this one as a delay or postponement differential. So this one earlier differential. So this is the difference between 2 differential. So postpone differential is they conduct the product segregation or product differentiate until late or supply change, delay. That's why it's called delay. So they may have some procedure, for example, to packing here, because they have not complete part yet. They need to do a different packing, because this one they need to do a proper packing here for power cord here to add in. So the procedure should be there to make sure all things pack together in the one box. Then should be not missing some cord or mixed with another cord to another country. But here they make a proper assemblies, and then proper segregation for each region, and then different transport. So the mixing can can monitor at early stage. But this one just do in the final process, but can reduce many things. Can reduce in terms of packaging, in terms of transportation, in terms of the logistic. So there is a pro and con for this easy differential and postpone or delay differentials. Okay, all right. That is another thing. But we go for the different thing now for the platform planning. Platform planning is the 2 simple information systems allow the thing to manage this trade-off. So the differential plan, they have a differential plan, they have a commonality plan. They have 2 plan. So for the differential plans, different in the product attribute from the customer viewpoint. But for commonality plan, they have the component which the product version commonly share, and the product version commonly share. And then therefore their physical are the same across the product in the platform. So you can see this example for the difference plan. You can see the plan explicitly represent the way in which multiple version of the product will be different from the respective customer, different customer of the market. So from this example, you can see that Havelock Packet provide product to the customer with a different need, like families, students, small office. So they have different target market. So this customer, they have different needs. So to serve this customer, Hewlett Packard developed three entire different products. For family, they have different attributes. For student, they have different attributes. For office, they have different attributes. So all these attributes separately different between needs or between these three categories. They have difference. So we call it differential plan. Differential plan. All right. For the commonality plan, this is commonality plan. So you can see here, they have a chunk, they have number of type, and then they have a families similar for the target, for the families, for the student, for the small office, but they have a common for the printer cartridge. They have common. They have a printer mechanism. They need two type of common for this one, so they use this one. So for this is how they can share the common inside the community plan for the printer example, instead of they decide different plan for each segment market. All right. So which one better? Which one better? You can have different view for this one actually, because different plan, they have different pros and cons. And then for community, they also have their different their pro and con for this model as well, because in terms of cost saving, but this one in terms of specification. For example, if they concentrate for student, maybe for a lot of production, they need to cater for the student. So maybe when we make a comparison with other printer in the market, for example, Hewlett Packard printer for student, maybe they're specific for the student, but for others model, for example, Canon, they don't do this one. They just concentrate on the commonality. So they cannot concentrate on the student. So they will produce different type of printer with different costs. So that's why the different target market also different need to cater. So they have different, what I call it, the segmentation can be influenced the production orders, the production quantity that they produce. So, but for the community also, they can produce a lot, but they will sharing maybe some casing. They have a similar casing for the family, student, and small office. But inside, for example, the cartridge, they have different cartridge for the family and student, but common office with the student. So that is how they do in terms of to reduce the cost. Because the student and office, then when they combine using the cartridge, they can produce a lot of the cartridge and then can give a more quality, more product or quality on that. So they can reduce the cost also for the cartridge. Maybe the cartridge can sell cheaper than this one. That is pro and con what we can discuss. But this one, when you go for the actuals in terms of working in real world, in terms working in the true company, you can have this what I call it chance to explore, well, to learn well how they do a strategies of marketing using this two differential plan and community plan. Okay, so like just now, I show you the printer. When we design the power cord, you can see here. This is logic board inside the printer. They just previously they just designed power with the printer come together. But instead of that, they just use the printer and the logic for the power supply just in one chassis, but the power cord can connect anytime from the outside. So like nowadays, so you can see the common cordless for laptop, for the printer, you can buy separately. But before that, in terms of design, they just consider for their power cord only for their printers, so they cannot share for another type of printers. For example, in this design, Hewlett Packard did there, even for family, students, office, they can share for different type of printer, but using the same power cord. So that is how the product design and development growth, using the what you call it, the architectures studies, so to separate, to make improvement based on that one. So guideline for the managing platform trade-off is the challenge. Before that, we go for the to see the challenge in the platform planning itself. So the challenge in the platform planning is to resolve the tension between the desire to the differentiate of the product and the desire of for this product to share substantially fraction of their component. So examination of the differential plan and the commonality plan just now reveal several trade-off. They have from the examination of the differential plan and then community plan, they have revealed some trade-off there. So for example, the student printer has the potential to offer the benefit to the small footprint, which is likely to be important to space conscious college student to use that. So, however, the differential attribute imply that the student printer would require a different print mechanism charm. So that's why they use a different ink, for example. So which is likely to add substantial to the investment, substantial to the investment required to design the different mechanism of the charm, to design the product to produce the printer with this different mechanism printing for the students. So this tension between the desire to tailor the benefit of the product to the target market segment and the desire to minimize the investment is highlighted when the team attempt to make the differential plan and community plan consistently. So we offer the several guidelines to manage this tension, So this guideline related is, for example, system level, related system level design issue, for example. The 4-step method for establishing the product architecture just now, like create schematic, clusters, and then geometry interaction. That is a step to establish the product architecture. So the guideline that early system level design activities. So you need to see at the beginning, at the design levels activities. So, but the many more detailed activities can be remained during the process as well. But that one you need to concentrate at the beginning. So We discussed some the issue that frequently raised during subsequent system level design activities and their implication for the product architecture. The applications such as defining secondary system, establish the architecture of the chunk, creating detailed interface specifications. Okay. So for the defining secondary, what does it mean? So the schematic just now, which when we do a schematic design, we need to show only the key element of the product. We define only key elements. So there is a defining secondary system. So there are many other functional and physical elements not shown, but some of which will only be conceived and detailed as the system level design involved. And then for this one, when we do establishing the architecture of the chunk, so some of the chunk are complex. So the complexity product may be very complex system, maybe very complex system in their own model, their own categories. For example, many of chunk in the design in the Hewlett Packard printers just now, so involve of dozen of parts. So you have show chunk of print like for the load of paper, for example. You just make a bulk of chunk that is loading paper, but inside that one they have many component inside that one, a dozen of parts involved to make that load paper tray. So that later you can make a what you call it detailed design on that one to after you establishing the architecture of that chunk. And then when you create the detailed interface specification as the system level design progress, the fundamentals interaction indicated by the line of the schematic. So you have the specification that indicate by dot line, by line from the chunk that is show the interaction. So the detail of the what you call it the flows, the interaction, that we collect the signal, that we use the material flow, that we use the exchange of energy. So as this refinement occurs, the specification of the interface between chunk should be also clarified during this creating interface specification. All right. To conclude that, we already learn the product architecture. We learn how to create the product architecture, the reason why, how to use it, what is the modular architecture. So what is their, what you call it, advantage, disadvantage. So this is another example. Instead of we just now focus on the printer, I just show you the trailer difference example for the modular architecture. So you can see here we have box, hinge, fairing, bed, spring here, wheel. So there is a clearly modular. So each part they have different function. So they have wheel to transfer load, spring to suspend trailer structure, back support cargo load, fairing minimize air drag, hinge to connect to the vehicles, box to protect from the weather. So that is a modular. So when you want in the what you call it, when you want to do innovation for the wheel, for example. You can take out the wheel and then you can not effect to another part. You can do a innovation, you can do a part changings for the wheel itself. So they just clearly indicate structure for modulars. But for the integral architecture, just now we see, you see the design here very different from this one. They have a, what I call it, very stylish. They combine some part to become function sharing. The most important part is the function sharing. They share the function. For example, you can see here, instead of here just to connect to the vehicle, when they do integration, they make aerodynamics design. They do a what we call it studies, not only to connect to the vehicle, they just using for the minimize air drag, because the design itself, and then ergonomic, stylish, aerodynamics, and then they have to what I call it, this one, suspend trailer structure. So there you can see the line here, they interconnected if others function as well. So there is the chunk, they connected with others, sharing the function. Not one chunk, they just have several functions. So here, for the modular, they have a strictly one chunk, one function. And then here, they have a different function sharing, and then they make a more stylish, combined material, more aerodynamic. So there is integral architecture design. All right. So what it is? What it is? So if you see this one, myself also cannot recognize actually this one what. But when we go through the textbooks, we see this one, nail clipper actually. So you see, this one is a modular design. Modular design. They have spring, just function to lift up the part when they pull down the clippers. They have stopper here. So this one cutter can be down, but the alignment controlled by this roller to make sure they go straight down. And then after that, they return back by the spring mechanism. That is the conventional and fundamentals on the clippers. But after several innovation, they use an integral design. This part become a spring function already, because this one should be written as this position as early before they this one push down. This one become a the what I call it, stopper here to push down here, and then this one will pull up, and then it will go down the cutters. There is a function, the what I call it, the functionality of the product same, but the chunk already combined, and then can get a more stylish design, reduce material, of course can reduce the cost. Even now you can make a $1 for this nail clippers, but this one maybe you cannot get. You need to buy maybe one state only have one, or one family sharing with another families, for example. So now everybody can have it, that one can have it, that one. So that is how the integral design can improve the design, can improve the cost, can combine the function, For example, spring function combined with this straighten function to make sure this function still there, but the components, the chunk already combined to reduce the cost, to reduce the manufacturing, to increase the productivity and quality of the production of the manufacturing. So modular product architecture, others example you can see here, like Swiss Army, they have a Swiss Army knife, they have a straight for one, they have one workman, they have different, maybe you not, I'm not sure you still know this one or not, but this is a Sony Walkman. They use a cassette tape recorder like this. This one tape. Now they use CD, now use USB, now use cloud. So this one already phase out, withdraw from the market. Product decline and then already withdraw. That is the life cycle of the Sony Walkman already. So, but the platform of architecture of Sony Walkman, they have very simple. They have one for the play tape, for casing, and then for the read the tape, the film to play the song, and then the logic box. That is all about the Sony Walkman architecture. So when we did the chunk design, very simple casing, tape holding. So that is how we build the platform. But from there, they do a several innovation. They come out with the CD players. They come out with they still maintain the shape like now, like USB, like handphone. They have still all using handphone right now, using the cloud. So no more using this product, but the architectures, the principles always there, and the combination, the innovation from there can lead to the more stylish, more innovative products. So, for example, another example for integral products, you can see now high performance mountain bike, for example, for the racing, and they have a wheel for high wheel performance. They have a different design for the chunk of the gear shifting, brakes. They're very stylish. So in terms of the function still there, but the performance very increasing to reflect with the demand of the markets. For the compact camera itself. So this one now several years ago, everyone used these compact cameras. Like they use films, but now before that they use film, they use digitals, and now they don't use this compact camera anymore. They use handphone with the camera's function. So that is how they integrate all these functions into one single phone. Handphone, internet, typewriter, computer, camera, all inside this one. So all come together with one hand. So that is how integral product architectures begin, and using the several innovation or performance review, they give a good product based on the customer demand, customer needs. And then we already learned about choosing the product architectures, how to choose based on product change, product varieties, standardization. We already discussed about performance, manufacturing cost, management, project management, system engineering. So the cost based on the standardization, based on combination, based on the what we call it, the elimination of the part of the chance, so we can reduce the manufacturing cost, we can increase the product variety. So all about the manufacturing DFM, design for manufacturing. So this one I said just now, we go for further topic for that one. So but we all discuss about these items. And then we also have another example here. When you buy a car for they have panel here. So some panel, they have a shape, but they don't have any function. So that is called add-on, add-ons. So when you buy, you will add the accessories for your car. So you plus some monies. So there is an integrated control panel. You can add everything there. So very stylish. So instead of before, they have a separate chunks for separate control panels, but they now integrated in the one place for the control panels. So now nowadays the car, they have a integrated control panel already. So very stylish, very useful. One button maybe can control several elements, several function. So like a wiper or signal, for example. So in the one, this one can make a several function or several movement. So before, maybe the design is different. So they have for signal, they have for wiper, they have button for left, button for right. But after the combination left and right, they can make with one button only. And then we can use for the wiper as well. So that is how they make a integration in terms of product. Using elimination or product architecture just now. And then another example for this one, modular or integral, integral architecture. So this one you can see already integral or integral. So integrated, but some element inside this one, they have still modular. For example, for the antenna, for example, they just go batteries. So, but for the casing, you can see they have with this nowadays they have a no button, they have touch screen. So that is an integral architecture design. And then the concept of integral, we already have learned this one. They have two categories interaction between chunk just now. They have first fundamental interaction from those corresponding to the line or the schematic that connect to the chunk to another. This interaction is planned, we call it fundamentals. And then we have another like incidental interaction. But in this case, we have system, subsystem, component. They have clearly interrelation or connection between several levels, system, subsystem, and component. But you can see here, interaction with chunk, you can have internal interaction, but across chunk also they have, for example, from this line, they can cross over to another line, another subsystem. There is a interaction across chunk. That is how integrals design or integral architecture can play a role to the cohesion plus interaction. So there is another ways, another performance, another plan can be did using the integrals product design. And then we already learned how to establish a modular architecture to create a schematic product and a cluster the element. This one, and then we have from there we can make a product type variety like a wash I said just now. We can do a several varieties based on the standardization, based on the clustering the product itself. So we can make several type. So this is a Havelock Packard photos we discussed. We have this all these type of printers. We have a paper load, come in, come out. So there is from here we can see how they design the schematic designer from this part. They get enclosure printer, provide structure support, cartridge, different chunk, different functions. And then the flow of force, flow of material, flow of signal. So you can see here, this one already the internal control, like user interface, but all go to control panel. There is a logic control. They communicate with the horse, printer, and then they, of course, they have power supply here. And then this one is for printing side, printing mechanism. This one for the printers. I call it shape for the enclosed printer to provide structure support for this one. Chassis, we call chassis. And then this one store paper, blank paper, this one. And then user interface, this one. And then at the back, we have a connection for power cord. So that is how we design the printer schematic. But this one, like I said, not fixed. After we design this one, we do a clustering, and we do a element clustering for this part. For example, we cluster as a mechanism part. We cluster this one for paper tray. We cluster this one for user interface. We cluster this one for the logic board. So after we clustering, we when you remember again about the product design, when we have before we start design, we did a specification. We need to come out with the concept. So from here we have a geometry layout like this concept geometry layout using the 3Ds, using the board, whatever. You can see the shape, you can see the height, you can see the papers, loading, cartridge, rollers. So that is how to indicate your product. We call it, this is a concept design, geometry layout. So you can have several concepts. So you can have several concept number 1, number 2, number 3. So you can do a push metric. You can do a what you call it, the voting set to see, do analysis to find out the best concept you can use in your design. So based on that concept, maybe you need to revise again this chunk or this clustering. You need to go back to eliminate all, or to add on more chunk here, more cluster. You can put more cluster here. Or this one not suitable, this one you need to put here. So this one can be arranged back later on based on your geometric layout or based on geometric design, based on your concept, before you can start your actual design. Because in this stage, in the early stage, process development stage, it's very important to get the concept and specification. When you get that one, you can go further for detailed design. You can go further for detailed design. Because the detailed design just follow the geometric, follow specification, what you decide. So you can have your good design based on your planning before, your schematic design, your clustering, your geometrics, your interaction. So this is all can generate the specification for your design. You need to have this one. You need to have the product architecture before you can start your design, because your design based on the concept, you decide using the product architecture, what we learned just now. Okay, so another part I already explained to you is a project management. development management. So based on this one, you can base team assignment based on product architecture. So this one is how modulars, how integrals, for example, modular, they involve in terms of planning, but for integral, they just concentrate on the integration of the part. So that is the coordination between team member is very important. For example, in the team one, this one, team one, they have a design for the crankshaft, flywheel, connecting rod, piston, lubricant, and engine block. There is the daily task they need to do for the team one. But you can see here, the team two, they have a integration here to do a same thing for piston, lubricant, and engine block. For the team one and team two sit together to finish this task and to make a proper arrangement based on the assignment given. So there is a teamwork correlation to do the integration for this particular part. And then you can see team 3, team 4. And then another part is called integration team. It's outside the green, this one. For the integration team, all team involved for the accessories, injection. So team 1, team 2, team 3, team 4, we come here to see everything for integration of this part. So these are very what I call it, every company, they have different style of managements, but different what we call timetable, different schedules, but they have a same on the basic modulars, in term integration, in term of design. They need to have a collaboration between team to another teams. So how you manage it, there is in term of they have brainstorm meetings. So how we conduct is a different way. So the important thing is how to make the thing is successful. To make the things happen, we need to collaborate, to do a collaboration, to collaborate by team, integration with the other teams to make sure the project, the product can be produced, can create the good design, can be manufactured the design. And then we also have a discussion between differential and commonalities. So I summarize here. We have just now in the printer, we have families, students, office. We have a commonality on the chunk and type. So we use a common on the cartridge, for example. There is a instead of a different section, different type of the market, we have focused on different product and different varieties, but we need to have also integration using a standardization in terms of commonality style planning. Okay. And then this one is just to show you the product model lifetime that I said just now. So it is just comparison between Sony, Aiwa, Toshiba, and Panasonic product model lifetime. And you can see Sony, they have a longer lifetime. For example, here they have a good 5 years for from 3 to 5 years. They have survival time for their product. So they start with the fraction surviving. So you can see different model, different curve. But this one not what I call it, a different model, different product, different maker, they have different. So just to show you the trend, product model lifetime comparison. So of course, you can see different product, they have a different year, but average Others you can see here 1 years only, 1.7 years only for lifetime. But if we can spend more than that after 1 year for product, we can have a survival time. But almost product you can see in the market, they have give you 1 year warranties. Why? Because they have already here, because all product can sustain a lot, almost 1.8, 1.9 years. So in between 1 and 2 years, there is the what you call it, the average lifetime. But after that, they go for the survival time. So when we give the warranty before or until 1 year, so that is common, because the product cannot, you can use until up to 1 year, but after that, they have several damage on the product, need to replace wear and test for their product. So that's why they already calculate. So there is product model lifetime for all model. They use the same costs, but the same average lifetime for others product as well. So they need to make this one to go more than 1 or 2 years to make sure they give 1 year. But some product they give 2 years warranties because they confident, because after that they have survival time. So depend. So when you see when you buy something, you see they give 3 years warranties. So they already confident their product can long life until 3 years, but after 3 years, then you need to do something to change something, because that is the common sense. So the type of modularity, we discussed this one, but I repeat here, there are 3 types of modular architecture. They have slot, this one slot, 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 slot. They have slot, they have for component, sharing, swap modularity, feed modularity, and mix modularity. These are for the slot. They have different name for the slot, but they have another type for bus modularity and sectional modularity. So just to give more input to you, this the type of modularity. So they based on this component sharing, but this one based on the cut to fit, and then this one based on mix. All right. And then this one another example exercise for audio system. So what you can see here, where are the chunk for audio system as accessories for they have cassette, they have tuner, they have antenna, they have cellular phone, they have microphone, they have power amplifier, CD changer, rear controls. So all this one can be a chunk, but inside this one they have several or dozen components inside this one to fabricate, to make sure this chunk can be a product. Can be a product. So our task when we do a designing, we need to segregate and cluster it from each chunk to make more what we call it, the more systematic with the schematic design, and then clustering, and then see the geometry, and then make a model, and then see the best model. That is what we should do before we start our design process. Okay. And then the product architecture is the scheme by which functional element of the product are arranged into the physical chunk. So we already understand on that one. And then the architecture of the product is the establishing during the concept development, in the early stage, the system level design development as well. And then product architecture decision have far-reaching implication affecting such things as product change, product varieties, components standardization, product performance, how they can manufacturability, and product development management. And then the key characteristic of the product architecture is the degree of which is a modular or integral architecture. So the modular architecture, they have different, each physical chunk, they have specific elements, specific function they just interact between their chunk and then their function only. But for the modular integral, they have combinations, they have integrations to implement across the chunk, and resulting they have they combine, they fix between each chunk. So that is the fundamental decision, whether integrals or modular architecture, what type of modularity, how to assign function to the chunk, how to assign chunk to the teams, and then which chunk to outsource. So we can answer all these questions by understanding the previous lecture I said just now. So you can choose which one, type, how, and then which product or which part to be outsourced. In my previous class in the manufacturing engineering, I also teach the student how to decide when you want to buy or to make the product. That's mean you need to outsource. So either you need to outsource or you need to make in your own factory, you need to decide. So for example, you get the quotation from your vendor is $10. And then when you make a calculation, when you do inside the house, you need you will loss around $12. Instead of you order from outside, you get the quotation $10, but when you fabricate inside, using your machine, using your manpower, using your materials, using your electricity, you need to pay total $12. So which one you need? Either you need to buy or you need to fabricate. In terms of logic, from the quotation and then from the calculation, you see there, you can get more benefit when you outsource, because $10 you can gain $2 from the difference. But when you see, if you do a further analysis as a manufacturing engineer, well, you can learn from my class. You can see that the feed cost you invest, for example, when you want to decide to buy or to make inside your factory, you can see your manufacturing capability. That's why the manufacturing capability is very important. If you have invest to buy a new machine, sophisticated machine, you already buy the machine. The machine already there. If you make order outsource from outside, that machine only used for another product, another elements to produce. But for the part you outsource, you no need to use that machine anymore. Fine. But the fixed cost in terms of revenue calculation, profit calculation, you need to pay either you use or you not use. If you order from outside, outsource, you need to pay $10. Is it $10 just now from the quotation? But the machine you already invoice, you already invest, you need to pay monthly installment to the bank, for example. So that one, either you use or not use, you need to pay. And then workers also, you need to pay because you already hire them. So instead of $10, maybe we'll increase for the machine fixed cost, another cost for the marketing, for the run the what you call it, overhead companies. So from there maybe $3 or $4. So you plus $4 to the $10 already, $14 you need to pay. Even you outsource, you need to pay not only 10 but plus $4 for the fee cost and then for overhead costs. So you need to pay around 15 or 14. So when you do inside using your machine, you calculate just now $12. So that's why buy or making decision is very important. So you can do a proper decision for outsourcing. So you can see there, it worse or not, you do a outsourcing. If not, you need to make a right decision because you already have capability. That's why when you work, you need to things using all those elements to make a decision. And then practical concerns. So we recommend the 4 steps just now inside the product architecture. Number 1 is the creating schematic design for the product. After we make a schematic design, we do a clustering, we create a rough geometry concept, and then we identify the fundamental interaction or incidental interaction. So that is what we do. We create it. So the planning, coordination, special attention is very important during this practical part. And then product architecture conclusion, you can have this when this method lead the team through the primary architecture decision, subsequent system levels, and detailed design activity will contribute to continue evolution of the architectural details. The product architecture can enable postponements and the delays and differentiation. We learn a delay differentiation of the product, which offer the substantial potential cost saving. And then we have architecture choice closely linked to the platform planning and the balancing, the differentiating and the commonality, differential and commonality when addressing the different market segment like student, families, office. There is a different market segment when with different version of product varieties. So due the broad implication of the architecture decision, so the input from the market, manufacturing and design are essential in this aspect of product development. So with that, I think that's all the about the product architecture today. So any question? I think you can write down in the chat, and then we have I can answer. We can discuss a little bit before we adjourn. If you have any question, if not, we just I can share another thing if you want. Please let me know.